Hello, Professor. My name is Mohammed Usman, and the paper that you assigned me for the oral presentation is titled as Automatic Knowledge Extraction to Build Semantic Web of Things Applications. The vision of Internet of Things is to connect all the things to the Internet and allow a wide range of innovations and opportunities in different application domains. There has been massive growth in this domain, but currently, the development of a single and global ecosystem of things that can communicate with each other seamlessly is virtually impossible. And to achieve the aforementioned vision of the Internet of Things, in which people and things are connected to each other at any time and any place, the interoperability at different layers is required. The initiative made by the Web of Things, W3C, intends to provide an interoperable infrastructure to simplify the access to smart devices and making them easily controllable via existing web. But unfortunately, the wide range of ontologies to represent the Internet of Things devices and their produced data hinders the efficient development of cross-platform and cross-domain applications. The development of IoT.schema.org, which is the daughter of schema.org, requires the identification of most relevant topics in the IoT domain. And to obtain these relevant topics in the IoT domain, we must develop an automatic knowledge extraction tool, because the manual processing would be challenging and require lots of human effort. Therefore, would be very time consuming. Let's talk about the challenges that are faced in the knowledge extraction. First is the long-term challenge to be addressed is the design of unified schema in a specific domain. And second is the analysis of the most common topics of ontologies in a specific domain. Also, to classify this topic which has been obtained is the one of the challenging tasks. To address these challenges, authors have presented some of the methods which will be discussed in the later slides. First off, the authors have designed a novel knowledge extraction tool which they have termed as KE for WoT to help the domain experts. This tool, KE for WoT, utilizes machine learning techniques, and they claim that this is the first time that somebody has ever utilized machine learning techniques in the classification or identification of topics in the web ontologies. Currently, they have targeted 3 domains, which is home, city, and weather. And they developed a corpus which is composed of 4,500 research articles from the different journals and conferences. They say that this tool is going to be really helpful for the creators of IoT.schema.org. In fact, the results that are obtained from this study has already been communicated to IoT.schema.org. Since the tool that they have developed is automatic, so the development time is sufficiently reduced, and the overall human efforts for creating the schema is diminished. Furthermore, they have provided the empirical evaluation after consulting with 23 domain experts. Here you can see the knowledge extraction method which this algorithm has adopted. The popular topic identification has been divided into 2 domains, into 2 parts. One is the analysis tool chain and one is the expert domain. As you can see in the expert, they refer to LOV for IoT catalog, and they select some of the ontologies manually. Meanwhile, the analysis toolchain performs a similar task in an automatic manner. And what it does is it calculates the frequency of the terms which are actually used within the ontologies. Then the algorithm which is called word to vector is utilized to convert these words obtained from the ontologies into a vector that is machine readable. In these words are obtained from IoT Corpus, which I mentioned earlier, which is composed of 4,500 articles from the journals and conferences. After the conversion of words into the vectors, the k-means clustering algorithm is applied, and the experts analyze these clusters from the k-means and assign a name to these topics. These topics are then further analyzed to identify the popular ones, and finally the results obtained from the analysis toolchain are aggregated, and a final list of regular popular topics are listed. Here you can see the conceptual process which KE for WoT follows. First one is the ontology selection, the pre-processing, vocabulary extraction, term extraction, frequency calculation, word to vector, k-means clustering, results aggregation, topic name assignment, and the popular topic identification. All of these processes have been covered in this previous slide. Next off is the creation of IoT corpus. As mentioned earlier, that the word to vector algorithm utilizes the text from the corpus. These corpus are created from several thousand journals and research articles, and they involve two main steps. One is the corpus creation, and second is the corpus processing. As you can see, that the number of retrieved scientific publication per IoT domains are 1,162 for smart home, 1,322 for smart city, 2019 for smart weather. To perform the evaluation and present the results, the algorithm is implemented using Python, using following libraries and scripts: Scrappy, Ontosopy, NLTK, and k-means clustering. This is the table which shows the most important smart home terms among 24 different ontologies. This must be kept in mind that the extraction of knowledge for smart home, for smart city, and smart weather was obtained by selecting different values of k. For smart home, the best results were obtained by keeping the value of k equals to 84. And you can see the important topic that has been extracted using this algorithm is the state, system, home safety and security, parameter, measurement, engineering parameters, appliance, actuator, ambient parameters, climate, event, metadata, health, network, and identifiers. The next off is the important topics related to the weather among 24 different ontologies. The best results for the weather knowledge was obtained by keeping the k value equals to 53. And the most important topic discovered after application of the proposed algorithm were water-related weather phenomena, weather observation and forecast, physical quantities and mechanisms, weather forecast sensors, sun influence states and phenomena, weather status, measurement, weather reports, physical thing, geospatial, sun influence states and phenomena, soil, time, atmosphere circulation, and the metadata. Similarly, we have the most important smart city terms among the 24 different ontologies, which were country statistical profile, smart city topics, dimension, transport and logistic, data collection, context, pipes, IoT, specification, services, metadata, transportation mode, public utilities and buildings, buildings and infrastructure, and economy. Here I would like to discuss the evaluation criteria that has been opted by the authors. First is the selection of ontologies. The 10 ontologies representative of 3 different domains in the IoT field are actually collected from LOV for IoT for evaluation purposes. And the most important ontologies in each domain are selected according to these criteria. First is the citation. Citation of the scientific publications describing the ontologies. By this they mean that higher the number of citation, the better the ontology might be. However, this criteria may not be applied and should not be applied for a recent publication. Next is the journal impact factor and the conference ranking. Better the conference ranking, higher the journal impact factor, the better the ontologies would be. And then is the ontology disseminated in standardization. And for example, W3C, WoT ontology, and ETSI, M2M, and etc. Also, they considered the criteria of ontology-based projects, as they consider that more impactful is the ontology when it is implemented in the industry or has some industrial partners. Finally, the 2 more criteria were domain experts' involvement and the ontology code. Here we present the results of the study. The evaluation investigates whether the topics identified by the KE for WoT are sufficiently descriptive to be applied to ontology or not. And here they employed the sets of keywords which are manually assigned by human domain experts as ground truth. The table you can see shows the percentage of similarity between the ontology between set of topics identified for KE for WoT and the ground truth. The keywords you can see are actually the results, which shows the KE for WoT was able to identify these keywords, and majority of these keywords in the ground truth made 66% of the total, from 21 belonging to the weather domain, 28 belonging to the domain of smart city, and 7 of the 10 ontologies were actually assigned to keyword match, and all 10 ontologies show at least one match. This brings us to the conclusion of this presentation. The proposed method KE for WoT studied IoT ontologies using WoT to WoT, and K means machine learning techniques, to statistically analyze the most common topics. The methodologies is applied to 3 IoT domains: the smart city, smart home, and smart weather. The identified topics from this algorithm were then discussed with the iot.schema.org meeting, and they allowed the findings of this research to be used within the IoT schema, and they also mentioned as this study could be the starting point for further investigation toward generation and integration of knowledge graph. Therefore, this KE for WoT algorithm is supposed to help the researchers to stay updated with the scientific literature and the content of the existing ontologies. Thank you very much, Professor.